welcome you all in this NPTEL online certification course on mechatronics. Today we are going to talk about the transfer function and frequency response. In the last lecture, I discussed with you the dynamic response of the system, of the first order system, second order system, and we have seen the various performance measurement parameters also. Okay, here I am going to discuss with you is the another way of seeing seeing the dynamic response of the system basically. Okay. It is another way of looking at it, where we basically transform our equations from time domain to Laplace domain and or S domain, and then we look at the response. Okay. And yes, we look at the response of course, in case of the frequency response. So, I am going to talk about all those things in this lecture. So, let us look at the system transfer function first of all. Suppose I have got an amplifier. For that amplifier, I can define a gain as simply output by input. Okay. So, what does this basically means that this actually means that suppose you have an amplifier with a gain of say 5, okay, then it means that for a given input of say 4 millivolt, the output which you are going to get that will be 5 millivolt. Okay. Sorry, that is 20 millivolt. Now, for many systems, the relationship between output and input will not be as simple as this one. Okay. It will be rather in the algebraic form. Okay. So, these algebraic form or differential equations, okay, they basically describe the behavior of the system with time, and if these are differential equation, they can be converted into the algebraic form using the Laplace transform. Okay. And so, basically as I said, we are moving that way from the time domain to S domain. So, the transfer function is defined as the Laplace transform of the output divided by the Laplace transform of the input. Okay. So, this is again way of defining the transfer function. Okay. And signal in time domain is depicted by f t, whereas signal in Laplace domain is depicted by f s. Okay. And in Laplace domain, we write the function always in capital letter, that is the universal convention, whereas in time domain we write it in terms of the small letter. So, suppose I have got a transfer function G s, and when this is subjected to input y s and output is x s. So, this is what is mean, that G s is x s by y s, and here we assume the initial conditions to be 0, that is 0 output with 0 input. If I take the example of say a transfer function. So, I can take a second order system, spring mass damper system, and for this system we say the dynamic equation is given by this one. Okay. After drawing the free body diagram, and if I take the Laplace transform for this, this is what I am going to get basically, and so from here I can find out the value ratio of the output by input. So, output here is x s basically and input is f s. So, this is what I am going to get. So, this is my actually the transfer function. Okay. So, what is basically Laplace transform? Okay. And these Laplace transforms are actually used to convert the differential equations into the algebraic equation. Okay. We can convert functions such as sinusoidal and exponential into the algebraic function of a complex variable s. Okay. And the differentiation and integration operations can be replaced by algebraic operations in the complex explain. It allows the use of graphical techniques for predicting the system performance without solving the differential equation. So, that is one of the very good advantage of the Laplace transform. Okay. And when we solve a differential equation using this method, transient and steady state component of the solution can be obtained simultaneously, which otherwise has to be done in the separately, as we have seen in the last lecture. So, let f t be a function of time such that say f t is equal to 0 for t less than 0, and the s is a complex variable, then say L be the operational symbol indicating the Laplace transform of a function. Then the Laplace transform of function f t is this is how it is given as represented by f s, integration 0 to f t e to the power minus s t dt. The process of finding the function f t from the Laplace transform f s is called the inverse Laplace transform. That is, if you want to come back from the Laplace domain to the time domain, what we have to do is that we have to perform the inverse Laplace transformation, and this inverse Laplace transformation is represented by this and inverse Laplace transform can be found by inversal integral like this. Okay. So, this way we can do the inverse one. So, the basic Laplace transform for the common input which we have seen in my previous lecture, such as say if we have a uniform impulse at t is equal to 0, it has a Laplace transform equal to 1, and if it is a unit step signal defined by say less than t for time less than 0, it is 0, and time greater than 0, it is 1. This way, then the Laplace transform for that is 1 by s. And for the unit ramp one, this one, okay, the Laplace transform is 1 by s square, okay, and for unit amplitude sine wave signal, Laplace transform is basically omega by s square plus omega square, okay, where omega is the frequency of the sinusoidal signal. Similarly, the Laplace transform for cos omega t will be s by s square plus omega square, and here Laplace transform for sin omega t is omega by s square plus omega square. So, there are certain basic rules in working with Laplace transform. Say Laplace transform of a constant into f t is equal to constant into f s, then Laplace transform of the two functions which are aided, okay. So, that is equal to the Laplace transform of two functions evaluated separately and then aided, and say Laplace transform of first derivative is s f s minus f 0. Okay. However, when we are defining transfer function, we take all initial values to be equal to 0. So, this one we can take equal to 0. So, Laplace transform of derivative will be actually s f s. Similarly, for the second derivative it is s square f s if we take this as 0, okay, and the Laplace transform of integral is a function, basically it is 1 by s of f s. And if we look at the inverse of the Laplace transform, so if these are the Laplace transform, here is the inverse of that. So, 1 by s plus a is e to the power minus a t, and a by s into s plus a is equal to 1 minus e to the power minus a t, and b minus a by s plus a into s plus b is equal to e to the power minus a t minus e to the power minus b t. Like that, s by s plus a whole square is this one, and similarly s a by s square s plus a is actually is equal to this one. So, now let us look at the first order system. So, this is the first order system as we have seen in the previous and lecture. Okay. So, Laplace transform for this with initial condition 0, I can simply write as a 1, this one I can write as s x s, this is a 0 x s is equal to b 0 y s. So, I can write the relationship between output x s by y s is equal to b 0 by a 1 plus s plus a 0. okay, or this can be written in this form basically G by tau s plus 1, okay, and where G is the gain of the system when there is a steady state condition, okay, and A1 by A0 is the time constant of the system. Now, if the first order system is subjected to say unit step input, then we can take this y s is equal to 1 by s basically. So, I can write this x s as g s y s. So, this is 1 by s, I am doing it. I can write it in this form, and if I take the inverse Laplace of this, then this is what we get. So, you see that by taking the inverse Laplace transform, we are coming back to the time domain. So, here what we have done, we have this expression which the first order system dynamic equation is in the form of a first order differential equation. So, with the help of Laplace transform, we converted it into the algebraic expression, and then after algebraic conversion into algebraic expression, we went back to the time domain by using the inverse Laplace transform. So, again resistor capacitor system is an example of the first order system, okay. So, we can write the expression for this one, and this could be simplified in this way. Now, let us look at the second order system. Okay. So, in case of second order system, the relationship between the input and output is given by this one, as we have seen in the previous lecture, where these A2, A1, A0 and B0, these are constant. Now, if I take the Laplace of this, this is a second derivative. So, this is basically s square xs first derivative. So, s xs, and here it will be only xs and ys. So, now I can find out the relationship between xs and ys, and it is this one. Okay. So, here you can see that we have a quadratic term in s over here. There is alternate way of writing this differential equation of the second order system, and that we can do by defining these terms omega n square and zeta square like this. And if I simplify, write this expression in terms of zeta and omega n, I can write it like this, and if I take the Laplace, and then I can write xs by ys is equal to this one. Okay. So, this way I can write, and if I subject it to unit step input, okay, then the transfer function for input is 1 by s. Okay. So, I can substitute in this one, and I can see the response for that. So, I have 1 by s term over here. So, this is my output in the S domain. Okay. This is my output in the S domain. I can write this always because it is a quadratic equation. So, there are going to be the two poles. So, I can write it in the form of S plus P1 and S plus P2, and where these P1 and P2 are the poles or the roots of the equation. Okay. So, I can find out this P1 and P2 value by equating this is equal to 0, and then writing the solution of this second order equation yes. So, this is what is that one, and I can simplify this one, this is there, and then I can take write the expression response for zeta greater than 1 in terms of the P1 and P2. Okay. And then by applying the inverse Laplace transform to the partial fraction, we can get back to the time domain. Okay. So, this is my expression in the time domain. Similarly, if I have zeta is equal to 1, then this is what my expression is going to be. So, these are my roots, both are going to be equal. So, this is my response in S domain, and again by partial fraction I can convert it into the time domain. Okay. So, this is how we get the response of the system in the time domain using the Laplace transform. Okay. Similarly, if it is a underdamped case, then this is my response which I am going to get. Okay, I can explain one example, say indicate the state of damping of a system having the transfer function this one and subjected to unit step input function. So, unit step input function means your Ys is 1 by s and Gs is xs by Ys. Okay, so, your xs is basically 1 by s and you can see that this is s plus 4 plus s plus 4 basically. Okay, so, in this case your roots are going to be equal this one. So, the roots are real and equal basically and hence the system is actually critically damped. So, this way we can tell the behavior of the system. Then let us look at the effect of pole location on the transient response. Okay. So, if we consider say a first order system is something like this and if input is impulse, then basically I can write this as 1 by s plus 1 because Ys is going to be 1 only. So, it is a if I take the inverse Laplace of this, then I will get the time response as this one. Okay. And what does this means that this means that as t tends to infinity your x is going to be 0. So, this is what it is and you see that this is s is equal to minus 1 basically. So, your root is equal to root is actually in the left half of the s plane or the pole is in the left half of the s plane. And if your transfer function is 1 by s minus 1 and subjected to unit impulse, then again this one I can write as this one or this axis will be 1 by s minus 1 and if I write take the inverse Laplace of this and go in the time domain, this is e to the power t. Okay. And this means that as time tending to infinity your response will be going to infinity. So, this is an example of basically unstable system. Okay. So, we can conclude that if your root is here in this case you see where is the pole s is equal to 1, it means that if your pole is on the right half of the s plane your system is going to be unstable and if your pole is on the left half of the s plane your system is going to be stable. Okay. So, this is what we can conclude from that. For a second order system similarly we know the response is this one. Okay, when subjected to an unit impulse I can that is Ys is equal to 1, I can write xs as this one or I can write it in terms of the two roots, okay, where p1 and p2 are the roots of the this characteristic equation. Okay. So, again here I can write these roots as this one as we have seen and depending on the value of zeta p can be real or imaginary and imaginary terms involves oscillation. So, that way we can predict the behavior. So, if I consider a second order system something like this, okay, so its roots are actually you can see that minus 2 plus j and minus 2 minus j over here and when this is subjected to unit impulse your axis is going to be equal to Gs, okay, and here if I take the inverse Laplace of this is what I am going to get. Okay. And so, in this case we can see that there is a exponential decaying envelope on this one, okay, on the sine function over here and this way oscillations are going to gradually decrease and your system is going to be stable. Okay. And if you have a root like this, okay, say this one, then your poles are basically 2 plus minus j Okay. When this system is subjected to unit impulse, again you are going to get axis is Gs, because for a unit impulse Ys is going to be equal to 1. Okay. And if I take the inverse Laplace of this is I am going to get the response. Okay. So, here you can see that we have a exponentially increasing term over here, and this is enveloping actually the sinusoidal function. So, that makes the system unstable. Now, we have seen the response of the system for a input. Okay. Now, as I said, the output from a system might be unstable, okay, or the response may be very slow, okay, or there may be too much of the overshoot. Okay. So, such system behavior can be altered by including the compensator. Okay. So, a compensator is a block which is incorporated in a system, so that it alters the overall transfer function of the system to get the desired characteristic. Okay. So, yeah. After seeing that, let us try to learn the frequency response. Okay. So, till now I have talked about the step input to a system, okay, but our input to the system could be sinusoidal as well, okay, and the sinusoidal inputs are important input in design and analysis of systems. Okay. So, if say the first order system which we have considered over here, okay, if I have a sinusoidal input like y is equal to sin omega t, this is how my system expression is going to be. Okay. Now, since the sinusoidal function have the property that when differentiated, the result is also sinusoidal with the same frequency. Okay. Thus, output is expected to be of the same frequency, but may be of different amplitude and the phase than that of the input. So, the frequency response is analyzed with the help of a phasor actually, and the sinusoidal signals are better represented by a phasor. Okay. So, for a sinusoidal, V is equal to V sin omega t plus phi, V is the amplitude and omega is the angular frequency, and phi is the phase angle. So, phasor can be represented by a line of length magnitude of V, making an angle phi with the phase reference axis. So, here you can see that you have a sinusoidal signal over here, okay, and say starting with initial phase angle phi, and say you have the angle related to axis OA, hence time this one. Okay. So, this is how it can be represented by a phasor of magnitude say V and the angle phi. Okay. So, as I was telling, so phasor can be described by a complex number, okay, and complex number is represented by x plus j y. Okay. So, here you have a phasor say of magnitude V and at an angle phi, this I can describe by complex number x plus j y. Okay. So, here on the graph with imaginary component as the y axis and the real part as the x axis, x and y are the Cartesian coordinate of the point which represents the complex number. We join this point to the origin to represent the phasor. Now, the phase angle of the phasor is represented by basically the tan phi I can take as y by x, and the length of the phasor is under root x square plus y square, and since x is equal to v cos phi and y is equal to v sin phi, I can write this v as x plus j y, and this is how it can be written. So, basically this is how I can represent a phasor as a complex number. Okay. So, here you can see the phasor. Okay. So, if complex representation of phasor say at here, so if it is say 0 degree, then this is basically 1 plus j 0 in the complex one. If it is over here, okay, so this is only j, real component is not there. Okay. And if it is over here, then we have the real component imaginary is 0. So, this is minus 1, and here it has got only imaginary, so minus j. So, here you can say that if the angle is 0, okay, or this is this one. So, when we are turning it by 90 degree, okay, we are getting this one. So, we are moving from the real to imaginary if we turn by it 90 degree, or imaginary to real. Okay. So, that way. So, the phasor equation, as we have seen, x is sin omega t. So, first derivative is omega cos omega t, okay, and this I can write as omega sin omega t plus 90 degree basically. Okay. So, what has happened is that the differentiation has resulted in a phasor with length increased by omega times, and it has been rotated 90 degree with the with respect to the original phasor. So, in complex notation, differentiation means basically the multiplication of the original phasor by omega, omega, as multiplication by omega will multiply the magnitude by omega, okay, and multiplication by j will basically the rotate phasor by 90 degree with respect to the previous phasor. Okay. Thus, this differential equation I can write as a phasor equation. Okay. So, this differentiation dx by dt basically I am replacing by j omega. Okay. So, j omega a 1 into x, and here this is a 0 x is equal to b 0 y, and this way I can write. Okay. So, this is my this one, okay, and my transfer function was b 0 by s a 1 plus a 0. So, basically what has happened is the frequency response function or frequency transfer function for steady state condition can be defined as the output phasor divided by the input phasor. Okay. So, the frequency response of the first order system if I look at, so this is 1 by tau s, tau is the time constant. So, in the frequency response what basically here you can see that what is done is basically this s is being replaced by this j omega. Okay. So, here what we do is that this is in the Laplace domain. If I want to go into the frequency response, I just replace this s by j omega over here, and then I find out the magnitude, I find out the phase of it. Okay. And for the second order function system, this is the transfer function. So, again frequency domain response function I can write here by replacing s with j omega. Okay. I can write it, and then I can write it of this form in the complex form. Bode plot is basically used for the frequency response. Okay. So, a set of values of the magnitude say g j omega and phase angle that occur when a sinusoidal input signal is varied over a range of frequency, and it is expressed by two graphs. Okay. That is, one is the magnitude versus angular frequency, and another is the phase angle versus the angular frequency. Okay. So, magnitude and angular frequency are plotted using the logarithmic scale, and such a plot is called the Bode plot. Okay. And magnitude is expressed in the decibel unit basically. So, this g j omega in decibel is written as 20 log g j omega. Okay. So, let us take an example of the Bode plot. Suppose I have got a Bode plot of a system having transfer function say k is equal to constant. Okay. So, the frequency response g j omega will be k only, and magnitude of that will be k only. So, in the magnitude in terms of decibel will be basically 20 log 10 k, and the phase angle is going to be 0. Okay. So, this is the plot actually the 20 log k, and this is the phase angle which is 0. okay, and this is the 20 log k. So, this is actually the Bode plot for this one, G s is equal to k. Now, if my G s is equal to 1 by s, then again I can find out G j omega as 1 by j omega, and I can write it in the complex form like this, and its magnitude will be 1 by omega, and magnitude in decibel is going to be this one, okay, or 1 by omega, or I can write it like this basically. Okay. So, if I plot it with omega, the magnitude, this is what I am going to get. Okay. And you say that at omega is equal to 1, this is going to be equal to 0. So, this plot is intersecting over here. Similarly, I can find out phase as minus 1 by omega by 0, okay, and so this is minus 90 degrees. So, I can plot it like this. And the Bode plot for the first order system, if I want say G s is equal to 1 by tau s plus 1. So, I replace this s by j omega over here, okay, and I write it in the form of the complex notation, that is x plus j y. Okay. So, I write it in this form over here, and then I can find out the magnitude as under root x square plus y square, okay, and this can be written in the decimal form like this. And so, the magnitude is this one. Now, here you see if this omega t is less than 1, okay, or what we can say that omega is very much less than 1 by tau, or omega t is very much less than 1, then what happens basically, okay, I can neglect this term actually. So, this becomes actually log 10 of 1. So, this magnitude is going to be 0. Okay. So, this is what I am going to get for less than 1 value, this magnitude is going to be equal to 0, and if omega t is going to be very much greater than 1, say omega is very much greater than 1 by tau, okay. So, this case the magnitude will be turning out to be like this, which is a straight line approximately. So, this is my plot. This frequency break point or the corner frequency, it is called, okay. And similarly I can have this one the phase also. So, this is my frequency response function. So, for the phase, for this is basically tan inverse y by x. If I do that, so it will be minus omega t, and we can see that as the low frequency, that is less than 0.1 by tau, basically this value is going to be 0, and at a higher frequency, okay, this is going to be minus 90 degree. Okay. So, this is what we are going to get, and in between this is for high value, this is for low value, and in between we can approximate with a straight line. Okay. So, the performance specification for the system can be given by the two parameters, that is the peak resonance and the bandwidth. The peak resonance is the maximum value of the magnitude basically. Okay. So, the maximum value of the magnitude over here, this is the peak resonance, and bandwidth is basically the frequency band between which the magnitude does not fall below minus 3 decibel basically. So, actually if this is the minus 3 decibel, so this is going to be actually the bandwidth. Okay. And this concept is basically we are going or is used in case of sensors, the bandwidth of the sensors. Okay. So, these are the references for your further reading. Okay. Thank you.